Just forgot to record. All right, so but another thing, and I'm only going to spend a little bit today on this, and then we're going to keep trucking. But how many of you, well, most of you have internet at home, right? Okay, how fast is your internet? Anybody know how fast their internet is? I need a number. What are you paying for? What's the number?
200.
200 what? Megabytes. Okay, you said megabytes. You got another one? Go ahead. 700 megabytes. Okay, you got two wrong answers. Next. Yeah. Megabits. What's the difference between a megabyte and a megabit? Okay, yeah, so that's correct. Do you know what the difference is? Yeah. Yep. So we have a scalar. So the idea here is, as a computer scientist, we don't want to be able to get taken advantage of at Best Buy. Okay, this happens less often than it used to, but it used to go into Best Buy when they had, like the still had 2 gigabyte hard drives, like by today's standards, small hard drives, unusable small hard drives. But back then they were considered big. But they would give you the measurement in terms of bytes or bits, so it looked like this gigantic number. It's like, bigger number must be better, right? Yep. So we're going to call this guy data sizes. And we're going to have 2 columns. So this is very similar to this idea of number conversions. So there's always a risk of data size conversions in any of my exams as well. So we have the idea of 1 bit. 1 bit is a single 0 or a 1. We got that covered, right? Over here, we have 1 byte is 8 bits. All right, so now let's just go down the bit column, because this is where our megabits per second internet connections live. All right, so we're going to say 1 kilobit, small b, usually small k as well. 1 kilobit is 1,024 bits. 1 megabit, small b, is 1,024 kilobits. 1 gigabit is 1,024 megabits. 1 terabit, which we don't really say that very often yet, but fast forward 3, 4, 5 years, we probably will, is 1,024 gigabits. Let's go in this other column. 1 kilobyte, big B, is 1,024 bytes. 1 megabyte, big B, is 1,024 kilobytes. 1 gigabyte, big B, is 1,024 megabytes. And 1 terabyte, big B, which we are used to seeing, kind of our hard drive sizes, that guy is 1,024 gigabytes. Now, we really only need to know 3 different numbers in order to create this chart, right? We need to know that difference between 1 to 8 to go from bits to bytes. And we need to know the 1,024 multiplier to go down the list. So when you have an internet connection that you're paying for that's 200 megabits per second, or as the commercials try to fake you out, they'll say, oh, it's 200 meg internet. Just throw the word meg out there. That could mean all sorts of stuff. All right, 200 megabits per second. When you actually start downloading stuff, you have a maximum theoretical speed. Now, if you want to start thinking about it in terms of things that maybe are meaningful to you when you've downloaded large files before, maybe you're thinking in terms of kilobytes or megabytes. So usually when you're looking at your download counter, you're seeing it in kilobytes per second. More commonly these days, our internet connections are getting fast enough that getting at least 1 megabyte per second isn't completely uncalled for. That does happen. So a 200 megabit per second connection is 200 divided by 8. Well, actually, why don't we walk up the tree and then we'll cut over. So we have 200 megabits is equal to 200 times 1024 kilobits, which is equal to 200 times 1024 times 1024 bits. All right, let's get that answer. So that's 200 times 1024 times 1024. So that gives us this number right here. Comes out to that, dude. 209.7 million bits. That would be a more impressive number, right?
Yeah.
On the commercials, yeah, it's 209.7 million. And they have to come up with some sort of cool kid way of saying bits. So that gives us bits. Now to get it over to the byte column. Convert to bytes, we're going to take that number, divide it by 8. And that gets us this. So now we're in the byte column. So this many bytes divided by 1024 gives us kilobytes. 25,600. Divided by 1024 gives us megabytes. So 25 megabytes per second maximum theoretical download speed. Now, most of your internet connections are what are called asynchronous connections, which means that your download speed is faster than your upload speed. Your upload speed for a 200 megabit per second connection might be something like 5 or 10 megabits up. Could be. Yeah, but it's smaller. It's a lower number. Yep. All right. So depends. Yeah, depends on how they're offering it. But typically for consumer-based internet, your download is faster than your upload because they don't want you running servers out of your house. And the reason I say here that 25 megabits per second is your maximum theoretical download speed is because your download speed is capped by whoever you're downloading from's upload speed. All right. So in order to get this full 25 megabytes per second, you would need to be downloading from a source that could feed it to you at 25 megabytes per second. Make sense? Where I would say it's uncommon for sources, especially when you consider that if you have a single server you're downloading from, it's you and your 10,000 friends that are all downloading from that same server. So their upload, in order for you to get your maximum speed, would have to be enough to do 25 megabytes per second times 10,000 to do that to everybody who's doing it. So we might say it is uncommon to be able to maximize your download speed from a single source. Let's call it, what is a solution? Anybody familiar with the technology that's used today to attempt to maximize your internet connection speed? Go ahead. Ethernet cable, that's our network thing that that's what the bits are traveling across. That doesn't tell us how fast they can travel across there. Not a piece of equipment. We're talking about software technology. Go ahead. Okay, and are any of you familiar with something that you can use that allows you to download from multiple sources at once? BitTorrent. Yep. So BitTorrent is an example of a technology that allows you to download parts of a file from various simultaneous sources. Now, unfortunately, in general, that idea of torrenting stuff has now had a connotation of being, oh, you're downloading illegal games, movies, yada, yada, yada. But that technology is actually the underlying technology, not necessarily how it might be commonly used, but that underlying technology is commonly used by people like Microsoft or any sort of video game when they release patches to distribute the patches to, because if you are downloading the patch from Call of Duty, let's say, they start distributing it, and the early people who are getting it are going to be getting it at a smaller trickle. And then all of a sudden they start sharing it with other people. So then you can start getting the patch more quickly. All right. Mm-hmm. Yep. But not just locally. Yeah. You become part of the network of people sharing stuff. All right. So our punchline here is that we should know what our internet connection, our advertised internet connection speed is, among other things that are part of our technological lives as computer scientists. But we should also know what it means. Make sense? All right, so now all of you know what your possible capability is if for when you find out what your internet connectivity speed is at home, you know what it's possible for you to download at. It's not 200 megabytes per second. It's actually 25 megabytes per second. And we can get to that by saying 200 divided by 8. That just allows us to jump straight across the column. We didn't have to go up the column, cut across, then go back down. We can see from this slide right here, if I'm sitting right here, in order to get to the exact same place over here, I will divide by 8. Similarly to if I'm sitting over here, I can multiply by 8 to get it in megabits. That makes sense? All right, and that covers us for data transmission stuff. It covers us for hard drive size. Why is it 1024 and not 1000? It's a multiple of something, but not a multiple of 8. In this case, it actually would be a multiple of 8, but that's not the multiple of 2. It's power of 2. Okay, so powers of 2, we talked last time, computers like binary, zeros and ones, base 2. So computers represent, when they create little memory storage things on the processor, they're called hardware registers, they create buckets, and those buckets must be capable of storing something that's a power of 2. It's just how the technology works because of digital logic. All right. So 1024 is the appropriate number when we're actually measuring bits and bytes and kilobits and all that stuff. It is not uncommon at a place like Best Buy for them to just do things in terms of 1000 because it's easier math, but it's technically not accurate. They probably don't even do the whole maybe thing. It's just fine. Okay, but officially that 1024 number is a pretty important number, but the concept of with computing, we're probably dealing with powers of 2. Okay. So this concept in here, this is something I'm not going to test you on directly as related to this class. But as I mentioned last class, every exam you ever have from me, regardless of the class topic, and we be class called basket weaving. There's always a risk, actually not even a risk. Every exam will have at least one conversion question on it. And that conversion question will fall into the category of something like this. How many megabytes per second is a 1 gigabit per second internet connection? Something like that. Or it'll be a conversion, numeric conversion like we talked about last time. Convert something from decimal to hexadecimal. Convert something from octal to binary. That kind of stuff. Okay, so 2 skills that you should get down now, because it's going to be 10% of every exam that you ever have with me, and you'll have a few classes with me. Because as computer scientists, this is a skill that we all should have, and it is related to programming in that when you write software that is moving data, you know, network-based software, moving stuff across the internet, how it's moving and the speed at which it's moving is important. That's something we should understand. Go ahead.
So it's either or different data sizes and
Yeah, whatever I feel like. It'll usually, in this class, it would be one question. In our, when I teach the computer organization class, you guys will have it next semester, 325. I might be teaching it next semester. Dr. Locklear usually teaches the undergraduate one. I teach the graduate one of that, but next semester it'll either be me or Blade. He's our new faculty member. We call him Blade. He's a Chinese guy. Yiming Liao is his name, but he goes by Blade. That's a whole hackathon story from a. So in a class like that, there's going to be more questions about conversions, data stuff, because that's what the whole class is about, that kind of stuff. All right. Questions about any of that? Go ahead.
how would you convert byte per second?
Well, I mean, it's the same. A byte per second would be the same number in bytes every single second. It's a byte per second is a transmission rate, where a byte is a size. But both bytes are the same byte. It just happens to be whether it's repeated every second or it's a single quantity. All right. Talked about that. I'm not gonna, I'll just briefly say this. We can do the same thing and figure out data sizes. You know, if you're looking at HD TV, 1080p TV, or now, you know, now most of our TVs are 4K when you buy a 4K TV. 1080p though, the full high definition resolution is 1920 by 1080. That's, you multiply those two guys together, this is the number of pixels that you have. Then you got to look at the technology and decide, okay, well, how much data are we using to represent each pixel? What's a pixel? A pixel is a little dot of light, okay, which represents a color. Well, the more advanced the pixel type is, the more various colors it can show. So let's just say it's a 24-bit pixel, which means that we're going to use 24 zeros and ones to represent a specific color of a specific pixel. So that gets us 49,766,400 bits for every picture we see on our TV screen. Now, let's assume that we're watching something at 30 frames per second. Standard TV is usually 24 frames a second, but 30 frames a second is pretty common for internet video and stuff, or 60 frames a second. But regardless, even 30 frames shows us the problem here. So when I say a frame is a single picture, and if you show 30 of those frames within 1 second, our eye sees it as video. Okay, so it's kind of like a flip book. You're looking at pictures flying by, it starts making it like an animation. All right, so that means in a single second, we're watching a TV show in full high definition with 24-bit color, we're looking at 1,492,992,000 bits. All right, every single second. Now, how do we watch data, whether it's streaming over the internet or older, when you have a cable TV at home, you have a little box that sits on top of your TV, right? Or below it, whatever. What does that box do? Other than just get hot? Go ahead. Okay, well, the video flows through that box, but that box performs an operation. Just like in here, we said a compiler converts from a high-level language to a low-level language. That box does a conversion. What does it do? Yeah. Huh? Decompresses. So the idea is that when we're sending data, in this case, video, over, whether it's the internet, whether it's over the coaxial cable network that the cable companies are using, whatever it is, however we're sending that data from point A to point B, what we do is we compress that data. We apply various software algorithms to it that make, let's say, 1 gigabyte of data behave more like 200 megabytes of data. We do something to it to squeeze it down into a smaller form factor. And then on the end, when it arrives, so that means it can travel, right? It can travel more quickly because the amount of data we're actually sending is a smaller compressed little chunk. But when it arrives at your TV set, in order for it to actually show up on your screen as video, it goes through that box. And what does that box do? It undoes that compression. So it takes that 200 megabytes and converts it back to a gigabyte in this example that it can then show directly on your TV set. There's a bunch of different compression technologies. All right, so concept for us as computer scientists is when we're sending data from point A to point B, one of the things we try to do to combat limitations on our data transmission speed is also try to massage the initial data into the smallest form factor we can get it into. Make sense? Okay, it's like when you buy one of those Tempur-Pedic pillows, and it comes in this little tiny package, and then you open up the package and it, all the air goes back into it and it gets big again. So it's kind of like that. You're not sleeping on it in a little tiny package. You're not going to get a good pillow situation there. All right. So this is kind of how computers work and how computer scientists work with data. Sometimes we repackage data only to then undo what we did on one end because we wanted to make sure it could get transmitted in the fastest time possible between point A and point B, even though we need the data in its original raw format on either side. Yeah, so I don't want to get too far into the internet connections, but generally speaking, your internet connection is measured 2 ways: maximum download upload speed, and then also something called latency. Or if you're playing your video games, it might show up as your ping on your video games. That's the amount of time it takes to hit the server and come back, the round trip of a single bit, let's say. So most gamers, even though in your mind, like, oh, I'm going to get the fastest internet in terms of download speed, your video games are not using very much of your download speed. They're using your latency. You're probably only sending, I don't know, no more than 1 megabit per second, probably far less than that most of the time. But you want it to happen quickly. That way, when you're playing one of your games, if it's a real-time game, like a first-person shooter or something like that, you are dead before you see the things move on the screen because you had long delays. All right. All right, so we've already talked about this: high level versus low level versus machine language. We looked at something like C++, high level language, power tool for humans. It gets converted to a low level language by something like a compiler, and we looked at Hello World in Linux. And then ultimately something happens from the output of something called an assembler that turns that assembly code into zeros and ones that ultimately the CPU runs. So we take our data in human package format, we repackage it through some tools until we get it into a format that the CPU actually can eat, can understand, can run. Same exact pattern we just talked about, right? All right. I'll briefly talk about this. Compiled versus interpreted languages. We've talked about compilers. They convert a high-level language into a low-level language, which then comes much closer to running directly on the CPU. And I just mentioned there's an existence of something called an assembler that takes it across the finish line to get it to actually run on the CPU. But we have another tool called an interpreter. Most of our programming languages today, in terms of the quantity of languages, are interpreted languages. So a common language that you're going to be exposed to in your 4 years here will be a language called Python. Very, very popular language, but it's an interpreted language. A piece of software exists that knows how to convert what you have said in Python into something that the CPU ultimately will understand. But that Python interpreter is probably written in something like C or C++. So these interpreters are written in a compiled language so that your people who invent languages can more conveniently come out with those power tools that maybe make your life a little bit easier. So if you looked up most popular programming languages 2018, let's say, and then you looked up most popular programming languages 2021, you're going to see our core compiled languages in there. You'll see C and C++ and Java and C#, maybe Swift from the Apple side of things. You'll see these core compiled languages, and those will be there forever. Very, very rarely does a new compiled language come onto the scene, and it's because compilers are very difficult to write. That tool for converting from a high-level language to a low-level language is a very complex tool, right? They're necessary for us, but you know what? If it kind of already worked, let's just leave it alone and maybe make those compilers even better. Just keep optimizing the compilers we already have. But if we want to provide better power tools to the programmer and say, look, here is a language that has some stuff built into it that make your life related to web programming, let's say, much easier, or your life related to game programming, much easier. They're going to give you a new syntax for maybe making those things easier through an interpreted language, because that interpreter doesn't have to do the job of converting from a language like Python down to assembly code. All it has to do is support the functions that the language provides so that ultimately it can flow through something like a C compiler, right? So they're much easier to write an interpreter. What's the downside though of an interpreter? If we think about this in real life, and I'll do it like based on a speech. So let's say that you're listening to some political figure from overseas, picking a language that nobody in here understands, let's say, whatever that language is. All right, so some foreign language that isn't common. We could have somebody, the version of a compiler would be when a news station here was reporting on the speech, they would have a version of the speech already converted into English, previously converted before the news station went on air. That's compiling, because we have something that natively runs on our CPU, English speaking brain in this example, okay? As opposed to what we commonly see happen is somebody's up there giving a speech in that foreign language, and then you have an interpreter that's in real time hearing words that are coming out of that person's mouth and turning them into something that an English speaker is hearing.
Or a better way, like speaking and then having the deaf interpreter.
With the sign language.
Yeah.
Well, yeah, I mean, that actually probably even drives the point home even more, because we might say that that idea of turning a natural language, a natural spoken language into sign language is probably even less efficient than converting German to English. I'm speculating, but it seems like it might be fairly reasonable. But the punchline here is that to convert German to English in real time is slower than if you had taken the German speech, spent your time before you needed that data, and converted it to English so that now you have it in a format that everybody already understands on the news channel or something. Okay, so in general, we would say, oh, well, interpreting things is slower than compiling things when we think about it being delivered during runtime, being executed. So in general, we'd say with computers, wouldn't we all agree that faster is better? Fair assumption, right? Faster is better. How do you measure faster? What does it mean for something to be faster on your computer? We talked about internet connections a little bit ago. Is 200 megabits per second enough? Are you going to spend extra money to get 400 megabits? Are you going to spend extra money to get the gigabit internet connection? 1,024 megabits. What's fast enough? We measure that by our own experience, right? If you were watching Netflix on a 200 megabit per second connection, and then you went to a different location and you watched that same show on a gigabit internet connection, as the end user, would you notice a difference? By some fraction of a second, maybe, right? So no, ultimately we'd be watching our show in full HD, no harm, no foul. The slower internet connection makes our end user experience the same as the faster internet connection. Kind of like having a car that had like a sports car that has like a V12 engine, that can technically go 0 to 1,000,000 in no time, but you're always driving at 30 miles an hour. You didn't need it, but you have it. Go ahead. Well, I'm sure the answer is yes, there will be some sort of max. But right now, right now we're ahead because right now the bottleneck is downloading, right? So it doesn't matter what they're selling us. We're only getting it from a single source at a certain speed. So why get faster internet? Because you might have multiple devices or multiple people sharing that internet in the house. You might have 2 people streaming Netflix in the house at once, plus somebody else playing video games, plus you're downloading something. Each one of those things will pull off the bandwidth that's being offered by your internet connection. In an example like that, maybe you would then notice that difference between a gigabit internet and 200 megabits per second internet because you have more things pulling from it. Yeah.
Doesn't that also build the quality of service then?
Well, that's more on the network side where they decide, okay, well, we want to make sure that our internet customers can stream Netflix over than them torrenting illegal movies. So that's what QoS is about, quality of service, where an internet provider throttles stuff. We do it here on campus, right? I'm sure none of you have downloaded anything illegal, right? Never. We haven't even heard of torrenting in here. Okay, but maybe you have a friend that's told you about this. When you start torrenting on campus, it might start off at a relatively fast speed, but then during the day, that speed will drop way off because we're throttling that speed so that our bandwidth on campus can be dedicated towards what's considered acceptable use. Email attachments and people doing web surfing, stuff like that, whatever it is, right? But you try to do something at 4 in the morning where there isn't a high demand for bandwidth, maybe you get a little bit better performance, something like that. All right, go ahead. We have a couple of different incoming connections for redundancy. I think we maybe have something called an OC3. I don't know what our total bandwidth is, but it's going to be, several gigabits per second, many of those. But keep in mind that's shared among 4,000 people on a daily basis. Now we're on that example of the 3 or 4 people in an apartment all doing something at the same time. We're on that kind of that example on steroids. Okay, no different than water coming to your house, right? If you get enough, if you go around your house and everybody turns the shower on and everybody turns the sink on, you're going to probably see a reduction in your water pressure, right? But if you have a big enough pipe coming to your house for the number of people that are typically using water at the same time, you won't see a difference, because actually your source of water pressure has more pressure associated with than your demand for water pressure. No different than what we're talking about here. We're just talking about data versus water. Make sense? All right, so I asked the question of how do we measure speed? Speed is in terms of the end user experience. If we think it's fast enough, if we don't notice a difference, we don't need more speed. Only when we start noticing something being slow. You start, it takes 5 minutes for your Netflix show to buffer. Something's probably wrong, right? Because usually you start the show, it might be a 5, 10, 15 seconds, and even 15 seconds, we're like, something's not right. You see the thing, little circles going, it's like it's loading. Well, is it loading or is it crashing? Whatever. But we're not very patient. But at the end of the day, if it pretty much starts streaming right away, we don't care what the speed was behind the scenes, right? So ultimately, speed is measured in terms of our end user experience. Okay. So would you say that our computers today are pretty fast? Yeah, our computers are fast today, right? In fact, we really can't get them much faster. Kind of this related to the question you asked, where, is there going to be some sort of limit to internet connection speed? That seems to be still trickling up, especially as we start replacing older transfer mediums with new. Now we're starting to move fiber directly to people's houses and stuff. So you're starting to see it to be more common for like gigabit per second internet. But what you haven't seen a major change in is the speed of an individual CPU over the last 5 to 10 years. 5 or 10 years ago, you could get a 4 gigahertz processor as your maximum speed. You could still do that today. So what have we done today? What are we doing instead of making a single processor faster? Multiple processors. You go back, 10, 12 years, you would have had a single core processor. Then it went a dual core processor. Then we had quad core processors. Now octa-core. Now you have server chips that have 48 cores on a single chip. That's 48 individual processors on this little tiny chip. Well, I mean, Moore's law would say that we keep doubling speed. Well, so what's our limitation? What is our current processors made out of? They're made of silicon. Okay, and the enemy of our current processors is heat. So if we make it go any faster, we have no way of dissipating the heat fast enough to avoid errors. And we rely on zeros and ones to be clean. We can't have errors in that data stream, right? So we're at the point now that if we turn the clock up, we overclock our processors to make them above what they were rated for, we start having too much heat, which leads to data errors. Now, some of the cool kids, what do? They try to combat it with like liquid cooling, submerging your entire computer in ether, which is an inert liquid, so it won't conduct electricity. When I was an undergrad, this was back when the speeds of processors were measured in megahertz. There was a guy down the hall who had overclocked I think it was a 200 megahertz Celeron processor to a gigahertz. And all what he had blowing on it was just a room fan. So and I was kind of the nerd on the floor, let's say. So at like 3 a.m, he's banging on my door. And I'm opening it, and I look down the hall. I was the first room on the right when you first come off the elevator. He was all the way down the left. And what I saw was the gates of hell. Flames billowing out of the storeroom. His entire room was on fire. There wasn't one place in that room that wasn't just completely ablaze. It was only because of old construction that whole building didn't go down. I mean, the building was just made of cement. That was effectively a, I don't know. Yeah, I mean, it didn't spread from that room at all. But man, don't overclock your processor. I mean, that was a, ridiculous what he did. But our high performance computer users today, we try to combat this by trying to find more and more aggressive ways of cooling, right? Cooling our stuff. But the reality is we're kind of at that limit of what silicon can take in terms of heat before it starts having errors. And we're also kind of at the limit of what we can do to dissipate it. So now we really have stopped making the clock speed faster. And now what we've just done is we've made more processors. But more processors doesn't necessarily, is 48 cores better than 2 cores? Well, only if we need to do 48 things at once. A single core can accomplish a single thing at a time. A dual core can accomplish 2 things at once. 48 cores can do 48 things at once. Now, it's probably relatively common that when you're using your computer that you might have 2 applications that are relatively active, 4 applications that are relatively active. Keep in mind, relatively active, I'm using the word relatively because we have to notice in order for it to be a benefit, right? So really anything more than a quad core in terms of normal computer usage, we're probably not going to notice. Because the chances of us having more than 4 applications that we're actually paying attention to is pretty low. So what's that 48 core processor for? Servers, where we have not just a single user sitting in front of the computer, but we have many users using that computer externally. Go ahead. Oh, we have to, if we want it to go faster. But I might argue today, do we need it to go faster? Or are computers doing things fast enough for us to accomplish what we needed to accomplish today? Probably for right now. So it's going to come down to what, especially with distributed computing, because now we don't even have to just do it in a single computer. We can link a bunch of computers together and have them all work on the same problem at once. And now that becomes the enemy of security, right? Because when we deal with security, we keep, you try to encrypt passwords. Well, we keep using more and more bits. Well, we use 64-bit encryption. We use 128-bit encryption, 256-bit encryption, a gigabit encryption. Well, a gigabit encryption means that there is potentially 2 to the 1024 possible, well, times 1024 possible passwords. Let's just say that's true. It's good enough for this example. That's a lot. Big number. Basically infinity for a single computer. But if you get 1 million computers working on that, and each of those 1 million computers works in a little, tries to guess the password for, just the, this guy's in charge of 10,000 passwords. This guy's in charge of 10,000 passwords. All of a sudden, that thing that we used to think was unbreakable because you were using gigabit encryption can now be broken in 3 minutes because you got enough computers working on it at the same time. Yeah.
You were talking about like having cores, like, so that means you have more applications. I was noticing on your computer that you have like a lot of applications.
Answer it with my screen. So I have 16 logical cores and 64 gigs of RAM. The laptop holds up all right for a while. But the answer would be no, because even though I have a lot of things open at once, how many things am I looking at right now? This, and I'm relying on the real-time recording in the background, right? Because I record the lectures. So really 3 things, 4 max, because I use this quite a bit to, do some quick math or something like that. So even though I have a bunch of things open here, or even though I think I actually closed some things earlier, but it's not uncommon for me to have, 40 or 50 tabs open just cause. I mean, I just open new tabs and I'm just too lazy to close them. So it's but I would say no, I don't notice slowdowns, but sometimes I'll notice a battery life problem if I'm not plugged in. Because, you know, one tab here is open to something that's like, you know, complete memory drain or was poorly written JavaScript on the web page. And, you know, I go from maybe, I don't know, 4 hours of battery life to, I don't know, 20 minutes, 30 minutes. Now, your question was, we're going to move away from stuff with silicon. Some interesting things. How many of you are familiar with Apple's M1 chip? So Apple makes their own processors. How many of you are iPhone users in here? I'm guessing it's about half. Okay, the rest of you are Android users. All right, so I'm assuming, how many of you are Android users? Oh my gosh, Apple's doing all right. Right. I use an Android phone. My wife uses iPhone. I write software for both. So well, but I'm running Windows on this, and I have Linux running at the same time. So it's one machine that I can run 3 or 4 machines on at the same time. I do prefer the Mac operating system, but mostly because it's a Unix operating system, not because I have some sort of affinity for Apple. Yeah. Mac. No, Mac. This guy right here is Spotlight Search. It's Command Spacebar. It's also the thing that I think it's a little, this guy right here. But I use a lot of keyboard shortcuts. I grew up with non-GUIs. No, I get it. I get it. But I mean, my affinity for Mac laptops has much more to do with it's Unix based. And I used Unix since I was like 9. I started programming when I was 9, and that's what I wrote it on was Unix operating systems. Yeah, so anyways, I was asking about Apple's M1 chip. Do we know anything interesting? Any of you have a machine with an M1 chip in it? Is that running M1? Okay. Did you have a Mac before that? Okay. You had a laptop before that. Okay. What's the biggest difference you notice with this versus your previous laptop? Okay. I'll give you the answer. The answer is battery life. The battery life on the M1 laptops is insane. If I'm on a Zoom call with this laptop, which has, you know, a high-end Intel processor, and so let's say it's an hour-long Zoom call. At the end of that Zoom call, I'm probably at, I don't know, 55, 60%, something like that. You know, the battery noticeably drained. If I have a MacBook Air that's running an M1 chip, and at the end of a Zoom call, I'm like at 98%. The battery life is insane on the for normal usage, normal like PC type usage. If you're playing a game on it, your battery life's going to go down all day long. But normal usage, the M1 chip is incredibly energy efficient, while still being very, very, very fast. So I think we're going to maybe see a shift in computer architecture, which might then give us, the heat thing might become less of a problem, because we certainly are moving towards having machines be more and more compact, right? So he has, is that an Air? So he has the 13-inch MacBook Pro with the M1. I have a 13-inch MacBook Air with the M1. So his is a little bit beefier machine, but my machine you can like dice onions with. Right, it's like super, super, super skinny. So, you know, we like our portable machines to be more and more portable, right? And then our desktops, that's if you're a gamer, you have your PC, you know, PC desktop that has all the horsepower, and you're, you know, got fans all over the place. It makes a lot of noise when it's getting going. We want our laptops to become smaller and smaller and smaller, which means we need to take stuff out of them. Fewer fans, because that means less noise, less weight, all this stuff. Well, now you got to think about heat even more, because now you don't have active cooling. You have passive cooling in your laptops to keep those chips cool. So I really think Apple making their own processors at this point. I think you're going to see some pretty cool stuff with what they're coming out with the M1 stuff. And pretty soon they're going to be announcing the probably M1X will be the next one. And then they're working on M2, which will be their more performance line things. Now that will then create a competition thing probably with Qualcomm. At this point, I'm not sure I see Intel jumping on the competition bandwagon there, although they should. But you know, Qualcomm being in the mobile space, if you're an Android user, your device is running Qualcomm Snapdragon processor, which is their version of that. Apple's chips are better. They're I would say a couple of evolutionary ticks better right now. Apple just has the lead there. Main reason I use Android, other than just personal preference, I have the Fold, which gives me a big screen. I watch a lot of video on my my phone, but is one feature, and that's sharing an internet connection, creating a hotspot. So those of you who are iPhone users, like, well, I can create a hotspot. I mentioned that my wife and I go on a lot of cruises. The thing that iPhone users can't do that I can do, you can create a hotspot that shares your cellular data connection with people over a Wi-Fi hotspot. I can do that too. What I can do is I can connect to a Wi-Fi connection and then share that Wi-Fi connection through a hotspot. So I can know the password and be connected to a Wi-Fi connection and then share that with other people around me, which allows me to, on a cruise ship, when you buy the internet package, it's usually on a per device thing. So I can be on the internet on my phone, share it. Now my laptop can be on the internet at the same time. Or I can sit at the wine bar and get free drinks because other people want to check their email real quick to talk to their kids, but didn't want to spend $150 on the wine pack or the internet package. Well, I mean, yeah, it's a hotspot extender, but it allows my source to the internet to be not just cellular data, but also another Wi-Fi connection. Just that one little feature is the deal breaker for me. And it's mostly because I want to have my laptop and as I sit on cruise ships, and my hobby on cruise ships is to write a piece of software during the ship that will pay for the cruise. Just a hobby because I program for fun. My wife goes off and does her reading and exploring the ship thing. I work on liver health. Okay. So punchline with all that, computers today are really, 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 really fast. And even though we can say, if you got down there with the stopwatch that's at the, you know, the microsecond level, a program that is compiled and running natively on the CPU is faster than that program running through an interpreter that then runs on the CPU. The question is, would a human notice? My argument would be for most applications, the answer is no. You won't see our high-end video games written in an interpreted language. They're written in compiled language because performance is very important to those. You won't see Photoshop written in an interpreted language because the performance of that is very, very important for like rendering things. All right, but something like a word processor. So if you are open source word processor person, you download it once, it'll run on your PC, run on your Mac, run on Linux, because it's actually running. A lot of them are written in Java. Java is kind of a weird kid in this example because Java is both compiled and interpreted. So Java is a compiled language, but it compiles down to a software-based processor called the Java virtual machine. So that means if they create the Java virtual machine for this, and they create the Java virtual machine for PC, and they create the Java virtual machine for Linux, any Java program that was written for the Java virtual machine can run on any of these computers because it's not running on the Intel processor here or the M1 processor on his Mac. It's running on the Java virtual machine that was already ported to those platforms. So Java is kind of this weird guy. It's kind of our higher performance way of getting business applications cross-platform, running on multiple different types of computers at the same time. But you still won't see high-end video games being written in Java. You know, you're not going to see the next PlayStation come out being a Java-based platform. It's just gamers expect latest, greatest graphics, explosions, blah, blah, frame rate. We're all about frame rate, right? You buy the newest, latest, greatest TV, you know, you want it to be 240 frames per second. I would say that 95% of the content you view, you won't be able to tell the difference between 240 and 120. Every now and then, there might be something you can tell the difference. Frankly, I would put it in the 90 percentile that you won't be able to see the difference between 60 frames a second and 240. Really, you got some people that are just very sensitive to it. It's like, oh, they can tell. It's just that little factor of smoothness. Like, I can't really see it, but I feel it. And sometimes there's truth to that. You know, their eyes just work a little bit better. But in general, human beings like big numbers. Faster the better. Higher frame rate the better. Whether it's actually benefiting us or not. All right. So that's how we measure speed. Ultimately, my argument is that speed is a measurement of end user experience a majority of the time. And if we don't notice it, it's slower. Who cares if it actually is? Make sense? All right. We're at 12:50, right? We're still good? Okay. All right, so let's take our first stab into a little bit of programming stuff. So the next type of thing we're dealing with here is that there are two kinds of programming languages. Very similar to this slide where I said there are two kinds of programming languages. We're looking at it through different angles. So we have compiled versus interpreted. We've talked about those. Now we have loosely typed versus strongly typed languages. And what we're talking about here is how do variables work? And this goes back to that slide about how do human beings solve problems? Memory, asking questions, repetition. We saw that slide, right? All right. So, and I said 100% of programming languages have facilities for those three things. So one of the things that a programming language, like we're going to be using C++ in here, that language has a facility for mimicking memory. It gives us a way of remembering things inside of our computer programs. So loosely typed versus strongly typed directly relates to this concept of how memory works, how remembering things in our programs work. A loosely typed, well, let's just start off with the concept of a variable. So variable is how programming languages provide us with the ability to remember a piece of data. Okay? It's called a variable. And I would usually refer to this as a name value pair. All right, so somewhere in your computer program, if you want to remember what your age is, you would create a variable named age, and you would put into it the value associated with your age, 18, 19, 20, whatever it is. Okay, name value pairs. So all programming languages will have facilities for mimicking memory, remembering stuff. Having said that, they will accomplish this in either a loosely typed or a strongly typed way. Typically, this is connected to the previous slide. Loosely typed languages tend to be interpreted languages. Strongly typed languages tend to be compiled languages. So what does loosely typed versus strongly typed mean? Loosely typed says when you create a bucket to hold a value, you do not have to tell the language what kind of value you're going to put in here. It's just a container that you can put stuff into. If I want to put a number into it right now, and in a few minutes, I want to instead put a letter into it, and a few minutes later, I want to replace that with a string, I can do that. Okay, this is a container for holding data that does not care about the data that's being that's stored in there. Well, it means something under the hood, but the programmer is not responsible for advertising what kind of data they intended to hold. Strongly typed languages are the opposite. When you create a bucket to hold data, you have to tell it exactly the kind of data that you intend to put in there. Now, I would make the argument that whether the language is strongly typed or loosely typed, it would rarely make sense for you to put one kind of data, one kind of datum into a variable and then change that type later on in the program. It doesn't make a lot of logical sense for you to do that. That probably means you need to have another variable. And that has to do with this idea of name value pairs. Typically, we're going to name our variables something that is meaningful to us, that describes the kind of value that lives inside that variable. Right? So if I create a variable named age, the expectation is it's going to hold a number. Now, could I create a variable named age and then put a string in there like the string Mike? I could. It's legal. I can legally do that. But now all of a sudden we've kind of broken the logic there. Because later on, way down in my program, when I go and I say, okay, well, which variable did I put my name in? Oh yeah, I put my name in the variable called age. Doesn't make a lot of sense, right? So it would be considered bad programming practice, even if it's technically allowed. So whether the language you're using explicitly makes you describe the kind of value you plan on holding in the variable right off the bat or not, you should have a very, very good idea of the kind of value you're going to store in a variable right off the bat, and you're probably going to stick with that kind of value. Make some sense? All right. So that's where maybe programming deviates a little bit from maybe how we might solve problems in real life, just because of the convenience of asking our computer for memory. So at home, it might not necessarily be that uncommon for, let's say you ran to Target and you got a Tupperware container and you decided I'm going to put shoes in this Tupperware container. And then all of a sudden, your wife decides that she's going to throw away all your shoes because you only need 1 or 2 pairs of shoes. Again, this is not autobiographical. So, so now we have an empty container. So rather than throwing the container out, we might repurpose that container for holding something else, maybe old tax documents or something like that. In real life, human beings might use that container for holding something for different things, just so we don't waste containers, right? But in a computer, we have subsystems that clean up memory, and it's very easy just to digitally run to Target real quick and ask for a new container. So good programming practice would indicate that we should probably create a variable with a name that indicates what's in there. And if we're using a strongly typed language, we're going to be forced to explicitly say that I'm going to store shoes in here. If we're using a loosely typed language, I don't have to, well, it won't let me explicitly say what I intend to put in there, but the name of the variable itself probably is going to indicate it. So if I name that variable box of shoes, I'm probably not going to expect to find tax documents in there. All right. With that in mind, C/C++, I'm kind of putting them in the same category for us right now, because we're going to start off basically writing our code in C, because we're not doing object-oriented stuff. And then we'll roll into objects. So C and C++, is a compiled and strongly typed language. That indicates to us that it is relatively fast. And when we create variables, we must define the kind of value that variable is built to hold. Yep. So we'll see. We'll see by examples here. When we say kind, we are talking about data types. And we'll see examples of data types. So here's the primitive data types in C and C++. If you want to put it in your notes, I can't get that plus to be on the same line, no matter if I shrink the. Whatever, good, nailed it. All right, so you could add to your notes that what I'm about to describe is the same in Java and in C# and in Objective-C and in Swift. Basically, this primitive data types I'm about to talk about here are the same for all of our compiled languages. Very, very, very little tiny changes in it, but generally speaking, it's the same. Why is that? Because all of our modern compiled languages came from C. So effectively, the language we're going to be using in here is the great-great-grandparent of all of our modern compiled languages. All right. So our data types are byte, short, int, long, char, and these are actually all lowercase, but just roll with it. Float, double, and then things get a little interesting. I'm going to just throw out here that it's the last one is called Boolean. This is the dude that changes a little depending on the language. Officially, C does not have a Boolean type. Booleans are true and false, so we'll be dealing with this a lot. Well, in C, we use integers. We use bytes, zeros or ones, to represent true or false. Starting with C++, we have a type called bool, capital B, capital O, capital L, that fakes that for us, but under the hood, it's still represented as a numeric type for human convenience. Yeah, you know, we like to say true or false better than 0 or 1. 1 being true, 0 being false. Actually, the rule is 1 being true, actually 0 being false, not 0 is technically true, but 1 is the one that's typically considered to be the true value. But it ultimately comes down to human convenience. And remember, the rationale for that is programming languages are tools that allow us to tell a computer what to do. Make some sense? All right, so homework. So we're going to do a short paper over the weekend, looking into these various data types. So we're going to say, write a 1 to 2 page paper detailing the different primitive data types that exist in the C programming language. So effectively, what I'm asking you to do is tell me what each of these are. And then we'll come and talk about that in detail on Tuesday. Yeah. That's fine. Just give me the data. Yeah, I don't care exactly how long it is, just long enough to give me what you need to say. And I'm okay with a bulleted list that says a byte means this. Make sense? Introduce yourself to this information, and then I'll fill in the blanks on Tuesday. Yeah. I don't care. However you want to accomplish it. Yeah, whatever you think is the best for you. Because at the end of the day, the job, you're not doing this for me, right? You're doing this so you understand the material. So go and learn about this material and put it on papers as evidence to me that you did the research. Yeah, I'll put it on Blackboard. So there'll be a Dropbox on Blackboard. Yeah. Would be what? For a string? Strings are not primitive types. Yep. Yeah. So technically in C, strings are char pointers. They're called char pointers in C, but don't worry about that for now. They're not primitive types. All right, I'll see everybody on Tuesday.